All right, in this tutorial, we're going to go through the process of doing layout versus schematic, or LVS, on our buffer example using a program called Netgen. Um, Now, unfortunately, when I went to do this for the first time yesterday, to do a dry run, I found that Netgen has apparently not been installed the um, on the USB drive that you all have. So you should be able to type netgen, and um, it should actually run it. I would not do the sudo apt install netgen. What I would do is instead is we're gonna go build it from source, and so we're gonna walk through that process first. It's very easy to do, and so we're gonna open up a web browser and go to opencircuitdesign.com, and then we're going to go to Netgen. And this is, by the way, a great place to look for information on Netgen under the reference in the tutorial section. But for the time being, we're going to download, and we're going to go with this tarball here. Just download that and save it in your downloads folder. It's fairly short. And we're going to look at the install instructions. It basically amounts to unzipping it or unarchiving it, cding into the directory, typing /configure make, and probably sudo make install. So that's all there is to it. So we're going to go through that. Here's my terminal window, cd downloads, and there's netgen 1.5166.tgz. That's a compressed tar file, and so I can go tar xfz netgen and tab complete, and now I should have a directory. There it is. So cd netgen /configure, type, and now it's going to configure for building. Then we do make, and now it's compiling. It's not a very big program, so it's done. And now we go sudo make install and put in the password. And now if we do which netgen, we have netgen. How about that? That's all there is to the installation. So like I said, it was in the install script along with all the other tools, so I'm not quite sure why it didn't actually install along with the rest of them. But fortunately, this one is not too hard to build given the setup that was put in place for everything, building everything else. So now the next thing that we need to do is generate a netlist from the schematic, from Xscheme. Okay. And so the schematic that is going to be comparable or directly comparable to our layout is the buffer.sch. Okay, so I'm going to open, and I put that in Documents, Inverter Tutorial, and it's buffer.sch. Okay. So this will have two instances of our inverter, and there'll be a subcircuit for the inverter, and then there will be basically these pin labels here will be used to fill in the names of the parameters that are passed to the subcircuits for the power and ground connections and for the input and the output of the whole thing. And so I can just click on the netlist button, and I can here edit the netlist if I like to view it, and there is the netlist. And you can see that this is buffer, it's called buffer.spice, which actually happens to be what the layout file was called, so we'll have to change that. But it lives in tilde/.xscheme/simulations. That is kind of the place where intermediate files that Xscheme creates tend to go. And so we're going to copy that file out of that directory and move it, let's say, into the same directory as our layout to do the LVS. That'll be the most convenient thing to do, probably, at least for the time being. So I'm going to close this down, and I'm going to cd.xscheme x cd.scheme simulations. All right, so I'm going to copy buffer.spice to, let's see, it's going to be /documents inverter tutorial layout. And we're going to call it buffer scheme.spice. Okay, so we have buffer.spice, which is the result of running x2spice in the previous tutorial, and we can open up both of those. Let's just take a look at them. gvim buffer.spice and gvim buffer xscheme.spice, and let's just do a kind of a run through of what these things look like. So our netlist extracted from the layout has a subcircuit inverter AYVPVN, and over here from the Xscheme schematic we have a subcircuit inverter AYVPVN. So that looks good. Inside of that we have two devices, X0 and X1. Here this one is XM1, XM2. They are basically Sky130 FDPR underscore NFET 01V8, and that matches what we see over here, so that's good. We have a PFET, and then at the top level we have here an instance X inverter O, X inverter 1, and that's an inverter. And here at the top level over here in the Xscheme schematic we have X1 inverter, X2 inverter, and they have, some internally generated nets, like net 1 is an internally generated net. Here we have inverter underscore 1/A playing that same role, and otherwise it looks pretty comparable. Now we're going to see some differences here. We can see that the NFET and the PFET have some parameters, and in the layout they're basically just numbers. By the way, the AD and PD and AS and PS parameters may be somewhat unfamiliar to you. They stand for area of the drain, perimeter of the drain, area of the source, and perimeter of the source. So W is width, L is length, but this AD, PD, AS, and PS have to do with the source-drain diffusion diodes, the drain-to-body and source-to-body diodes. So those will be used to model things like the capacitance of the source and drain diffusion regions. And in I believe the way things are set up with the PDK that we have, the units of these things would be AD and AS would be in square microns, and no. Yes, so these are going to be in square microns, and the PS and PD are in microns. And so those are extracted from the actual geometry of the layout. So they are, what you draw. Whereas over here in the schematic, they are computed based on the width of the transistor and some sort of fixed constant. So these are meant to approximate or stand in for what the area and perimeter of the source and drain regions might be based on how wide the transistor is. But they are not as, if you like, precise as they would be obviously from the actual physical design of the system that you get from the layout. So these kind of stand in for what they might be in the ballpark, and they're computed based on the width and length parameters. Whereas over here they're numbers. Okay. So anyway, they look promising. And the way that we do layout versus schematic comparison, in its simplest form, is we just run netgen. And again, it's kind of a TK console window. And we basically type LVS for layout versus schematic, and then the two net lists, buffer xscheme.spice and buffer.spice, and we hit return. And what we would like to see at the end of the day is something like netlists match uniquely. Result, circuits match uniquely. Okay, so that's good. When that doesn't, when we don't see that message at the end of the day, that usually means that we have some reconciliation to do. But you can see that you get some reports here, like the first circuit, which was the one that we listed first in the parameters we passed to the LVS command, contains 2 devices in 5 nets, whereas the second one contains 2 devices in 5 nets. And we get some information about what those devices are, and if things didn't match, it would basically show you the results of what it was able to match up. So you'll get sort of device classes that are sort of partially matched by the number of different things they're connected to and whatnot. Now, there are some property errors that it was complaining about, and those seem to have to do with the fact that the parameters AS, PS, AD, and PD in the xscheme schematic were computed and not simple numbers. And so I'm going to have to iterate with Tim Edwards about what he recommends to do in cases like this. There may be some sort of settings that we can put in place that allow it to ignore those sorts of property errors, or we may have to redefine what those parameters are in the schematic to be reflective of what they are in the layout or something like that, or maybe we can ignore the property matching for certain parameters. It's also complaining that there are certain parameters that are listed for, let's say, the schematic netlist that are not present in the layout netlist. Like, for instance, there's the M parameter, which is the number of the multiplicity of the transistor, how many unit devices are connected in parallel. There's a parameter called NF, which is the number of fingers. If you cut a device up into multiple strips and you stack it, kind of like we talked about, you can represent that through the number of fingers property. And so those parameters just aren't present, and so it gives us a message that says that they're not present in the one, whereas they are in the other one. But this output here is also logged to a file, comp.out. So if we were to exit Netgen and we were to list these files out here, you can see there's a comp.out, and it basically contains that same stuff with maybe slightly more information about the subcircuits and things like that, and the pins and whatnot. But anyway, so that's what I'd like to see from you. For if you like include this comp.out file as an appendix to your report, or take the text and paste it into the report or something like that. You can format it with code block or something in LaTeX if that's what you want to do. But that file should be, if you like, the stuff you submit for the LVS part. Anyway, so that's a brief tutorial. You can go to the Open Circuit Design website and see the Netgen page. And if you look under tutorial, you get kind of a nice description of the algorithm. And he runs through, strangely enough, a buffer example, which is actually because I poked him back in 2012 or something like that when I was teaching this class, and this was an example that I was working up, and so he was kind enough to put together this tutorial in response to some of my questions, and so it's a good resource to look at. It goes into some detail about kind of what's going on and what to do when it mismatches and things like that. Okay. There's also a reference section here, which tells you, what some of the different commands are that you can run besides just the LVS option. So Netgen is actually kind of an interesting program. It actually was written by a guy named Massimo Civilotti, who was a student in the same lab that I did my PhD in, only he was kind of in the group of students, or the batch of students that were in the lab before me. And he wrote Netgen as a tool for, as part of his PhD thesis, which is on kind of a field programmable chip for making prototype analog VLSI circuits, sort of like an analog field programmable gate array equivalent. And this would have been back in the late 1980s. And so Netgen also did netlist comparisons, and so that's primarily what we use it for today. But it also has capabilities for netlist translation and had some things to do with his proto chip. Anyway, we'll hear a little bit more about Massimo Civilotti when it comes time to do MP2. Anyway, that's it for this tutorial. Hopefully it will help you finish up MP1, and we'll see you next time.